Hello everyone, this is Wang from Princeton University. Thanks for coming to my presentation. Today I'm going to introduce my research, the Series Voltage Compensator for differential power processing. It is a category of converter architecture which can achieve highly efficient voltage regulation for DPP systems. So up till now, differential power processing has been effectively implemented in lots of modular DC energy systems, such as solar energy systems, battery systems, and storage or computing servers in data centers. In these systems, numerous identical loads or sources are connected as a large-scale array. Each load or source unit consumes similar power with similar load profile, which makes it a great fit for differential power processing. So let's take the data storage server as an example. In the data storage server, the hard disk drive array is distributed into different groups. Each group contains similar number of hard disk drives with similar power consumption, as shown in the blue bar on the right. The red bar here shows the differential power among different groups, which is a small amount compared to the load power. So in a conventional voltage step-down architecture, all the hard disk drives are parallel to the output of the DC-DC converter. In this case, full load power needs to be processed by the DC-DC converter. However, if we stack different groups of hard disk drives to a DC bus, the voltage can be stepped down by nature, so the voltage conversion stress is eliminated. To keep the voltage balance of each group of hard disk drives, we only need to process the differential power, which is a small amount compared to the full load power, so the energy efficiency of the system can be significantly improved. One challenge of the DPP architecture is to regulate the input DC bus voltage. In DPP systems, where the series loads are directly connected to the input DC bus, the stacked DPP string voltage is fixed to the input DC bus voltage. The tightly coupled load voltage and bus voltage might deteriorate the system performance. For example, in data centers, the DC bus voltage in a server rack may change between 48 volts to 54 volts. But IT equipment needs precisely regulated voltage to function properly. In other cases, such as the solar panel array, the stacked string voltage needs to be adjusted in order to achieve maximum power point tracking, but the DC bus voltage of the inverter on the grid side is relatively fixed. Therefore, a voltage regulator is needed to decouple the input DC bus and the DPP loads. The most straightforward way of implementing this regulator is to utilize a standalone DC-DC converter cascaded as a front stage. In this case, however, the full load power again flows through this DC-DC converter, so the partial power processing advantage of the DPP system is weakened. In this paper, we proposed a series voltage compensator architecture for the DPP voltage regulation, namely SVC for short. Different from the cascaded standalone DC-DC converter, the SVC is only connected to the top several voltage domains of the DPP system. In this example, it is connected to the top first voltage domain of the DPP system. In terms of the power rating of the SVC, the input current of the SVC is the same as the DC bus, but the input voltage of the SVC is only a fraction of the overall input voltage. Therefore, SVC only processes a portion of the overall system power, and the major power is directly delivered to the load. Leveraging this partial power processing concept, the SVC can generate much less power loss than conventional cascaded DC-DC regulator. This slide shows a few different ways of implementing the SVC with trade-offs in voltage regulation range, control complexity, and component count. In the first three topologies, the SVC is implemented separately as a DC-DC converter, and in the last one, the SVC is merged into the DPP converter as one extra port. The first one is a Buck-derived SVC that applies to the cases where the input voltage is higher than the DPP load voltage. When the input voltage is lower than the DPP load voltage, the SVC can be designed as a boost converter, which is the second topology. The Buck-derived SVC and the boost-derived SVC have very low component count, but they only regulate the input voltage towards one direction, either up or down. The third one is a boost-derived SVC that regulates the input voltages in both directions. It requires more components and a more complicated control, but it offers a wide regulation range. The last one is the SVC implemented as an extra port. The input current of the extra port can be bypassed through the DPP converter. The control cost of the extra port can be reduced by merging it into the main controller of the DPP converter. So one way to evaluate the performance of different SVC topologies is to figure out how much power processed is related to the SVC. It can be generally classified into two categories. The first, of course, is the power processed by the SVC itself. The SVC processed power can be evaluated by normalizing it to the total input power, denoted as rho SVC. Since the output of the SVC is directly delivered to the top several body domains, it will cause power mismatch and increase the differential power processing of the DPP converter. Normalized increased the DPP power and denoted it as rho DPP. The summation of rho SVC and rho DPP represent the total SVC related power processing. If it is lower than 1, the total SVC related power processed is less than the input power, so it is better than standalone regulator in terms of lower amount of processed power. If the summation equals to 1, it is equally good. If the summation is larger than 1, it is worse. This slide shows the normalized SVC processed power in different cases. Here is the input and voltage and current analysis of 3 SVC circuit implementations. Assume that the DPP system has n-series stacked void domains. In this figure, the output of the SVC is connected to the first void domain as an example, but it can be extended to the first and second void domains or even more. Denote that the output of the SVC is connected to the top k void domains. Then the input voltage of the SVC can be obtained, and the normalized SVC processed power can be derived accordingly. The normalized SVC processed power of 3 example circuits can be unified as one equation, and the MV here is the voltage regulation ratio, which is the input voltage divided by the DPP load voltage. The rho SVC in different cases can be drawn in this figure. As we can conclude here, as the number of series stacked void domain increases, it helps decrease the SVC processed power. But as the regulation ratio increases, it will increase the SVC processed power. Similarly, this slide shows the normalized increased differential power caused by the SVC. When the SVC power is delivered to the top k void domains, the part that surpasses the load power of the top k void domains will be delivered to the other void domains. Accordingly, the increased DPP power can be obtained. This figure shows the rho DPP in the DPP system of 6 series stacked void domains. It can be concluded from this figure that there is no additional differential power processing if Vin equals VDPP. If the regulated voltage difference between the input voltage bus and the output voltage load becomes larger, the increased DPP power will be higher. But if the output of the SVC is connected to more voltage domains, that is K is larger, then the increased DPP power will be lower. In this paper, we select the Buck-derived SVC as an example, build a prototype of it, and applied it to the MAC-DPP converter. The MAC-DPP converter, as shown here, is a single multi-winding transformer-based DPP converter, which can achieve ultra-high efficient differential power processing with militarized size. Besides the partial power processing, the Buck-derived SVC also has the advantage of soft body startup of the series stacked void domains, and it can cut off the DPP loads in fault conditions by simply disabling the upper switch as shown here. The normalized total processed power of the Buck-derived SVC will be always less than 1 if the regulation ratio MV less than 2, which means as long as the input voltage less than 2 times of the DPP load voltage, the Buck-derived SVC will always have advantages over conventional cascaded regulator. To verify the previous analysis of the SVC processed power and the increased differential power, we performed a Monte Carlo simulation in SPICE. In the simulation, the input voltage of the DC bus is 65 volts. A Buck-derived SVC is utilized to regulate the input voltage from 65 volts to 50 volts for a DPP system with 10 series stacked void domains. The load power of each void domain is a random variable which follows a uniform distribution within the range of 0 to 10 watts. The simulation executed for 10,000 times, and each time the processed power of the SVC and differential power of the MAC-DPP converter is recorded, and their probability histogram is plotted as shown on the right. This figure shows the statistic histogram of the SVC process power and the total input power. It indicates that the power rating of the SVC is significantly reduced by shifting the curve leftwards. This histogram plots the differential power of different voltage domains. The blue one is the dB power of the voltage domain that is directly connected to the SVC, which is in general higher than that of the other voltage domains. It indicates that the SVC connected voltage domain indeed needs to process more differential power. This slide shows the complete setup of the experiment test bench. In the experiment, we applied our SVC and MAC-DPP prototype to support a real hard drive storage server. The hard drive storage server containing 50 hard drives and divided into 10 series stacked voltage domains. Each voltage domain supports 5 hard drives with 5 volts, and 10 domains require 50 volts. As shown here, the MAC-DPP prototype is a 10-port DPP converter coupled by one single transformer, sitting in the center. The size of it is only 3.5 cm by 4 cm. The SVC is connected in series between the MAC-DPP converter and the input voltage bus. It regulates the input voltage and output precisely 50 volts for the DPP system. The SVC size is only 1/4 of the MAC-DPP size, comparable to a US quarter, and the maximum power rating supported by the prototype is 450 watts. This slide shows the top view of the test bench as well as the measured waveforms of the prototype. A DC power source is implemented as the DC voltage bus in data centers. It outputs 60 volts, and the Buck-derived SVC can effectively regulate the input DC voltage from 60 volts to 50 volts for the series stacked HDD array, as shown in the waveforms. We measured the converter efficiency of the SVC and MAC-DPP prototypes, and the overall system efficiency in different cases. In the experiment, the series DPP load voltage is fixed to 50 volts, and the input DC bus voltage changed from 55 volts to 65 volts. The left figure shows the system efficiency with different input DC bus voltages. It indicates that the system efficiency decreases as the Vin increases. It aligns well with the analysis before because both the SVC processed power and additional DPP power will be increased as the regulation ratio increases. The right-hand side figure shows the separate SVC converter efficiency and the MAC-DPP converter efficiency, as well as the total system efficiency. The power processed by the SVC prototype and the MAC-DPP prototype are also labeled along the curve. As we can see here, both the SVC process power and the MAC-DPP process power is only a small fraction of the total load power. Benefiting from the partial power processing, the system efficiency can be significantly improved from the converter efficiency, which is close to 99%. In summary, in this paper, we have proposed a series voltage compensator architecture for the DPP voltage regulation. Leveraging the partial power processing concept, the SVC only processes a fraction of the total load power, generating much less power loss than that of a conventional standalone cascaded regulator. Different circuit implementations of the SVC were presented and compared. Two metrics were defined to evaluate the performance of different SVC topologies. A Buck-derived SVC was selected, built into a prototype, and was applied to a 10-port MAC-DPP converter. Besides lower power rating, the Buck-derived SVC can also achieve soft voltage startup of the series voltage domains and can cut off the DPP loads in fault conditions. The full system was tested on a real hard drive storage server, and it achieved 98.8 peak system efficiency when delivering power from 55 volts bus to 5 volt hard drives. That's all for my presentation today. Thanks for coming.